Okay, let's go to chapter 20. This is second law of thermodynamics. One of the definitions for second law of thermodynamics is in this way. If you have, right, these two objects, correct? One at this temperature, let's say T1 equals to 80 Celsius and T2 equals to 20 Celsius, right? What happens? Well, we have heat transfer, remember? From the hot object to the cold object, right? So, and this is the second of thermodynamics, right? Heat flows spontaneously from the hot object to the colder object. Second of thermodynamics. We have more definitions, but let's start with the first one. Okay, when we're dealing with second law of thermodynamics, also we relate this to the efficiency of a heat engine. We have a heat engine. A heat engine is defined as this device that converts heat into mechanical work. And we have mainly in the analysis three types, right? Heat engine. We have three types. We have steam, we have gasoline, correct, and we have diesel. We have these main three types that we analyze in general in this chapter. Steam, gasoline, and diesel. Okay, let's go to the steam, right? Let's say this is one. Okay, let's do it. So the idea is to have a huge container of substance, right? Internal energy, correct? Another one with hot temperature and the one with cold temperature. The idea is to keep constant heat, the heat transfer for a long time. Remember, if we have small objects like this one, like that one we did before, right? In this case, the heat rate is not constant, right? It's not constant, but if this is a huge reservoir, and the amount of heat that is transferred from here to here is not too much, right? We take that rate constant for a long time. That's the idea, okay? So this is the picture for this. This is a hot reservoir. We have right here the heat engine, and we need, right, a cold reservoir, right? This is TH and this is TC. The same thing happens right here, right? TH, right, and TC. And this is the heat engine, right? Right here we have a substance, right? A substance. The working substance is right here. Could be again steam. It could be vapor of gasoline and air, right, and so on. Perfect. So now we need heat transfer from here to here, right? The same thing right here. This is a picture one more time. This is, imagine that we separate these two objects and we connect these two objects by a heat conductor, correct? Now heat is conducted from here to here. Now we have something inside that it makes work, correct? That's the idea. So we represent this in this way. So we have heat coming from this hot reservoir, right? It's represented by this heat going to the system. Also we have heat leaving the system, correct? Or going into the cold environment, correct? And then work is done. Perfect. Now, when we use the first law of thermodynamics, what do we have? We have the energy is conserved. So this energy is converting to work plus this energy, right? So what do we have? Heat, correct? Well, we can use also this way, okay? And later we apply the first law of thermodynamics. Okay, QH, just QC, by the way, right? QC, QH, correct? Is equals to work done by the engine, right, plus QC. I remember we use the convention that heat entering the system is positive and heat leaving the system is negative, correct? Now, to represent this in this way, right, we take this as the absolute value, because later we're looking for the work done, the net work done by the heat engine, right? Heat engine is equals to this heat coming from the hot reservoir minus this heat coming from the cold reservoir. Perfect. Now, when we're dealing with heat engines, in theory, we pay attention on cycle, right? We are dealing with the cyclic process, correct? So we are starting one point, right, and we go to the same point, correct? We make a cycle. When that happens and we apply the second law of thermodynamics, the change in internal energy is zero. Okay, let's apply that condition right here. Right, applying this first law of thermodynamics, right, changing internal energy equals to heat, right, minus work. In this case, we're dealing with the engine, so work done by, this is the net work done by the engine, right, and this is the net heat, correct? This one is the net heat. Now, in this case, right, we found that this is zero for one cycle, is zero, and then what do we have? This heat is equals to the work done by the heat engine. But what should be this heat? That's the net heat. And what is the net heat? Well, the net heat is equals to heat, right, coming from the hot reservoir minus heat, right, going to the cold reservoir. Correct? Perfect. Now, using these quantities, let's define efficiency. Efficiency is defined, that's the symbol for efficiency, E, is defined as the work done by the engine, right? Actually, this is the thermal efficiency, okay? Divided by the input heat, right? Input heat, correct? Divided by the input heat. But what is the input heat? The input heat is gonna be QH, right? So this is equals to work done by the engine divided by QH. Okay, now let's go back and substitute this value, right? Heat, work done by the engine right here. And what do we have? Let's find then the efficiency for this case. And then we have that efficiency, efficiency is equals to work done by the heat engine, which is equals to QH absolute value minus QC absolute value. This absolute value is used, right, again, to avoid the condition that when the heat leaves the system, heat is negative. Correct? Perfect. And then divided by the input heat. Great, and what is this? This is equals to 1 minus QC over QH. Perfect. Now, this is again the thermal efficiency, taking into account heat coming from a hot reservoir and going to the fraction to a cold reservoir. Okay, it's better to use, instead of heat, it's better to use temperature. It's coming in. Okay, perfect. Now, let's continue. So we define then efficiency in this way, correct? So efficiency is equals to 1 minus QC over QH, right? Another statement for the second law of thermodynamics says that the efficiency for any heat engine cannot possible to be 100%, right? We cannot get 100% efficiency according to the second law of thermodynamics, or a statement, second statement for the second law of thermodynamics. Correct? Perfect. Now, let's see what happens when we are going in the opposite direction. Again, we have right here a substance in this picture, correct? And also, we are dealing with a cyclic process, so we can represent maybe this in this way, correct? Look, in that way, in that way, in this way. That is a cycle, imagine. So this is the H, right? This is QH, right? QC, right? And TC. And we have work done, right? That's the heat engine. Now let's go in the opposite direction. We have machines that work in that way, and those are, for example, the refrigerator or the heat pumps. Okay, what happens to the refrigerator? Well, we have to do work to move heat from a cold object and send it to a hot environment, like the kitchen in this case. Okay, and it works in a reverse process. Again, now in this case we have, this is TC, right, and we have QC, correct? We have the refrigerator right here, so work is done, right, and you send this to this QH to a hot reservoir, right? This is the case for a refrigerator. It goes in opposite direction, right? Refrigerator. Perfect. Now, what should be the efficiency? Actually, the efficiency for a refrigerator is called the coefficient of performance, right? Coefficient of performance represented by K in this book. Perfect. Now let's find the coefficient of performance or efficiency for a refrigerator and later for a heat pump. Okay, let's do it. So right here you can see for this efficiency is going down, right here is going up. How do we define the efficiency? Right, actually again, the books call it this coefficient of performance, right? Coefficient of performance, correct? And in this book is K, and represent the efficiency. But how do we define efficiency one more time? Well, it's not right here, but let's define it. Efficiency equals to work divided by input heat, right? Input heat, work done by the engine. Okay, this is right here, but here is the reversed. Means this is equals to input heat, correct, divided by the work done by the engine. But what is the input heat in this picture? The input heat is gonna be QC, right? So equals to QC over the work done by the engine. So this is the efficiency for the refrigerator, right? Or coefficient of performance K, right? Coefficient of performance K is equals to QC, right, over work, correct? Well, also we can continue. Let's use, for example, conservation of energy right here to find work done. We can do it. For instance, we can say that from this picture, these two combine to create QH. So we can say that QH is equals to work, correct, plus QC. Absolute value, right, to avoid signs, right, because it's gonna be, remember, when work is done on the system, work is negative. When work is done by the system, work is positive. Okay, to avoid that, we represent this in this way. Perfect. Now we're looking for the work done by the heat engine. So work is equals to what? Heat. Okay, H minus heat C. Correct. Perfect. Gonna be the opposite of this one. Got it. So what do we have then when we substitute this value? Okay, I'm right here, right? Coefficient of performance, right? K is equals to what? QC. Okay, absolute value divided by QH, right? Minus QC, absolute values. Or just like this, in this way. And this is for a refrigerator, right? Refrigerator, coefficient of performance. It goes from 5 to 6, right? The number, this ratio. Okay, what about for a heat pump? A heat pump relates these two quantities, right? When we're dealing with a refrigerator, right? This is the input, right? For heat pump, this is gonna be the input. It goes from, let's say, the environment to the house, right? It's heat pumps, these devices that send heat right to a house or a building. Okay, perfect. In this case, the picture is gonna be the same. The coefficient of performance for a heat pump correct? K is equals to the same as the definition, right? For efficiency, correct? Efficiency is gonna be now heat input, right? Because it's inverse to the traditional heat engine, right? Divided by work done. In this case, what is the input? The input is gonna be, right, this QH, and this is equals to QH over work done. Okay, so we have another coefficient of performance. This for heat pumps, right, is gonna be QH over work, correct? This is for heat pumps. Heat pumps. Perfect. So as you can see, coefficient of performance is very important in this analysis of the second law of thermodynamics. Now, let's go to the other case, or the special case when we have the maximum efficiency possible, right? When do we get the maximum efficiency possible? Well, when we use the Carnot cycle. Carnot cycle is the cycle that represents the maximum efficiency. Perfect. And this is the picture for this cycle. Okay, we have Carnot cycle. In this case, we have, let me see, I need more room right here. Hopefully you have no room right here. Okay, like this. Perfect. We have two isotherm and two adiabat, like that. Okay, we start right here, point A. We're going down to point B, which is this point C, correct? And goes back because we're dealing with cycles. Remember, in this analysis, we're dealing with cycles. Okay, perfect. This is D and so on. Okay, so we have heat is added right here. Heat. We simulate the same picture as this picture. I remember right here. Now right here we have the adiabat, the isotherm and the adiabat. So we have heat going through this system, right? The working substance, and heat is removed, and we have work done, right? Work done by this system. Okay, let's find the net work done, right, in this analysis. Okay, let's do it. Remember that work equals to what? When we have cycles, well, is the area under the curve. That's gonna be equals to the work, right? The net work done by this heat engine. Okay, let's do it. Let's do it. One more time. This is called. This is the isotherm. Isotherm. This one, also this one, and this one is adiabat. Right. So we have two isotherm and two adiabat. Of course, we have volumes right here. Remember, this is PV diagram. This is V initial, V final, correct? And this is what? Pressure, right? Pressure. Correct. Okay, let's do it. Let's do it. Again, let's find this work, the net work done by this heat engine. The ideal is an ideal one, okay? Carnot cycle. Let's do it. So for the isotherm, okay, let's find, let's say, what is the heat added? The heat added right here. Let's label this 1, 2, or 3, correct? 1, 2, or 3, or just work done from A to B. What is the work done from A to B? Well, this is an isotherm. We already know from the previous chapter, right? The formula for the isotherm, correct, for the work done is equals to N, right? And what else? N times R, TH in this case. Let's call this TH again. Isotherm, this is TH because it's harder than this one, right? This is okay, this is TH and this is TC. Perfect. Better. Okay, great. TH because we are in this isotherm times what? ln of volume final over volume initial. Perfect. What about the work from here to here, from B to C? In this case we have area, but also we know the formulas for that part, right? The work from B to C is equals to, remember when we have adiabat, it means heat equals to 0. Okay, if heat is equals to 0, we use the Phys law of thermodynamics, which says changing internal energy equals to V minus work. Correct? Now, in this case, what do we have? If heat is 0, correct? So heat is equals to what? Heat is equals to negative the change of internal energy. But how do we define internal energy? Remember, internal energy is equals to N what? N R, correct? No, N CV delta T, right? That's gonna be the internal energy. So in this case, what do we have? It's equals to negative, plus negative right here, right? N, right? CV delta T. Perfect. What about the work done from C to D? Okay, from C to D, the same thing, right? This is isotherm, and we have the same formula, right, as before. It's gonna be nRTC, right? Ln of final minus initial, so V what? VD over VC. Correct? Perfect. Now let's go to I need room right here, more room. Where? Oh my God, let me go right here. Let me write this part too. Okay. Now let's go from D to C. This is another adiabat. For adiabat we have this formula, correct? So gonna be work equals to what? To N negative, or it's gonna be negative N CV delta T. Correct? CV delta T. But look, this one, look, this one equals to negative and CV, what else? What is the final? The final is TC minus T what? TH, correct? What about this one? This is negative N CV, that's gonna be, the final is TH, right, minus TC. Correct? Or equals to what? This equals to N CV TC minus TH. So these two are opposite, right? These two cancel out, correct? For adiabat, right, if this work is positive, it's gonna be negative, and they cancel out, right? As we can see right here, right? It's the same quantity. This is negative, and this is positive, so they cancel out. So what should be then the net work? The net work is only this plus this. Got it? Okay, let's do it. So the net work is equals to this plus this. So the work done is equals to N RTH, right? Ln of what? VB over VA plus, right? N RTC, correct? Ln of VD over VC. Okay, now let's work with these quantities. Okay, this V over A, right? This V over A right here, and BD over BC. Okay, let's work with those quantities. Perfect. In this way, let me erase this part. Correct. This is the last equation that we got. Correct. Perfect. Look, let's use adiabat. Correct. These two, we have these two, correct? Look, this is V and this is C. Let's use temperature, okay? What should be then the Austrian adiabat? Let's say TH, correct? Times V, what is V right here? V what? B, right, to gamma minus 1 is equals to Tc, correct, to Vc gamma minus 1. Okay, perfect. Let's see what happens between these 2 points. The same thing, right? Gonna be T what? T H times V A gamma minus 1, right? At this point, correct, must be equals to what? The part right here, right? Using adiabats, right? It's gonna be equals to Tc Vd gamma minus 1. Correct? Perfect. Now let's divide these 2 quantities. So Th is cancelled and Tc is cancelled. And what do we have? Well, we have right here, look, let me do right here, correct? V B over VA, correct? Gamma minus 1 is equals to Vc, correct, over Vd to the gamma minus 1. The idea is to find how are these 2 related, these ratios of volumes, using these conditions and from adiabats. Okay, let's do it. So what is the conclusion from here? Well, we have that B over VA must be equals to Vc over Vd, correct? Okay, now look, let's see, this one correct? V over A, right? C over D. Perfect. Now, let's now find the ln. Okay, ln right here, right? Must be the same thing, ln right here. Correct? Perfect. But I want to find something like this. Look, from here we have that ln V over VA must be equals to negative. I'm switching right these 2 volumes, right? ln of Vd, which is this one, over Vc, correct? Can you see it? Or we can call this, right, this quantity equals to this, right? Like that. So this is equals to negative, right, this one. Okay, perfect. And then what do we have? Look, let's go back to this final work. So work is equals to, this one stays the same, right? And RTH, and then VB over VA. But look, this one is negative of this one. So this is gonna be minus nRTC, correct? ln, correct? VB over VA. Now these 2 quantities, right, can be rearranged in this way. Perfect. Now what do we have? Well, that the net work done for this Carnot cycle is equals to nR, correct, TH minus TC times ln VB over VA. Correct? That's the network. Of course, we have heat coming out. We're gonna be C, right? QH and QC. Okay, the same idea. Got it? Okay, so this is the work done in this cycle. Now let's find the efficiency. The efficiency, we call this the Carnot efficiency. How do we define again efficiency? Okay, let's go. Let's go back and let's apply the definition for efficiency. It's right here, right? So efficiency is equals to the work done by the engine, which is this one, and RTH minus TC, ln, right? What else? ln times VB over VA. Perfect. Okay, perfect. Imagine. Great. Divided by what? But input heat. What is the input heat? Is this one, right? QH. It's gonna be, look, QH. But what is QH? One more time. When we're dealing with the Phys thermodynamics, right? We define the internal energy, changing internal energy equals to heat minus work, for example, right? But how do we define this changing internal energy? Remember the definition for changing internal energy, right, is equals to NCV delta T, correct? But along this path we have an isotherm. Isotherm means T constant. So if the T is constant, the change is zero. If the change is zero, right, the changing internal energy is also zero. So it means what, that this is zero. So in this case, heat, right, the input heat is equals to the work done on this process, correct? And what is the work done in this process? Well, it's gonna be this one, right? It's gonna be nRTH over ln VB over VA, correct? Perfect. Now let's do it right here. So what do we have? We have that 10, this is divided by nR, correct, TH ln VB over VA. And what is this? Well, this is just TH minus TC over TH. Perfect. Over TH. All this is equals to 1 minus TC over TH. And this is the famous Carnot efficiency. That's the maximum efficiency a heat engine could get. This one. Right? So actually, another statement for the second law of thermodynamics is not any heat engine, right, can go farther than this efficiency. Actually, the efficiency is less than 100%. Second law of thermodynamics. Perfect. So we got then the efficiency, correct? Carnot efficiency, that's the maximum efficiency, 1 minus TC over TH. When this is maximum, right? When TC, well, remember these are in Kelvin, so this should be or must be absolute zero to get, right, 100% efficiency in this cycle. Got it? Okay, perfect. We have more cycles, right, that are in this analysis. We have the gasoline. Let's try to go to the gasoline one. Hopefully we have enough time because the videos are kind of short. Okay, let's do it. Let's do it. Okay. Oh, by the way, before going to the next topic, look, we have these efficiencies. When we compare this to this one, what do we have? We have the 1 minus QC over QH must be equals to 1 minus TC right over TH. Perfect. From here, what is the conclusion? QC over QH, right, is equals to TC over TH. Let's rearrange it this way. Look, we have that QC over TC must be equals to QH over TH. Correct? It's like similar than when we have the this quantity at the beginning is equal to this quantity at the end. It's like a kind of, right, conservation of a quantity, right? Because this quantity at the beginning, this quantity at the end. So this quantity is very important, right? And this is called the entropy. Later, the next topic, right, is coming. It's gonna be entropy, right? Entropy. The symbol is S. Correct? When we send this term to the other side, what do we have? We have QH over TH minus QC over TC is equals to 0. Correct? And this is the change, right? It's a change. This is equals to the change in the entropy. This is 0 only for reversible system, right? We are dealing with ideal cases that where we have no friction, nothing, and the system is reversible. When that happens, the change of entropy is 0. But later, when I see that when we involve friction, of course, this is greater than 0 because of friction. Okay, perfect. Let's see. Okay, let's stop right here for now at this part one for the second law of thermodynamics, and see you in part two. Okay, thank you. Bye.